Good morning, everybody. We're wrapping up the semester. We got 2 more chapters left. Chapter 7 has 5 sections. Chapter 8 has 4. And we have 3 more weeks. So we're going to pick up the pace a little bit. All right. Chapter 7 deals with decimals, percents, and real numbers. The first section we're going to look at is called Terminating Decimals. The word decimal deca means 10. Deci means 1/10. So we're looking at here is decimals. We're looking for all the numbers after the decimal point. You have numbers in front of this. So for example, 2.35 is also read 2 and 35 1/100th. Because when you read decimals, you always go to the furthest one. That's the units amount. So remember, everything to the left of the decimal are the numbers. They're all base 10. So this is 10 to the 0, which is 1. 1 times 4 is, that's just 4. This next number is in the tens column, 10 to the first. The next number, 10 to the second, is in the hundreds. And then it keeps on going from there. Thousands, 10,000s, 100,000, 1 million, and keeps on going. So the further to the right, the smaller it gets. So after 10 to the 0, then we have negative numbers. 10 to the -1, 10 to the -2, 10 to the -3, 10 to the -4. In mathematics, a negative exponent simply means move the position of that number and drop the negative. So if I have 10 to the -2, that's the same as 1 over 10 to the second, which is 1 over 100, which is called the 100th. So this is the 10th, 100th, 1,000th, 10,000, 100,000, and so on and so forth. So the part means it's a decimal. So this number will be read 2 and 35/100th, 10th, 100th. So numbers can be written. Let's say we have a number 10.475. This one could be written, you have a 1 in the tenths column. You have a 0 in the ones column. You have a 4. This is after the decimal. This is now goes to negatives. Then we have 7 to the -2. Then 5 times 10 to the -3. Any further would be negative. So what this number looks like is 1 times 10, 0 times 1. I'm just converting these to numbers. 10 to the negative first is 1 over 10. 10 to the negative set 2 is 1 over 100. This one's 1 over. Remember, if your base is 10, the exponent tells you how many zeros you have after the 1. All right, so it's 10 plus 0 plus 4 over 100. 4 over 10, 7 over 100, 5 over 1,000. Ten plus 0 is 10. Since the biggest denominator is 1,000, we have 4. We have to add one more 0. So we multiply this one by 10 and this one by 100. Why 100? Because it has 1 0. We need 2 more. So there's the 2 zeros. So it's 400 over 1,000, 70 over 1,000, 5 over 1,000. Since they're all over 1,000, we can add the top numbers. So it's 400 plus 70 plus 5 is 475 over 1,000, which makes it 10, since it's solid numbers. Since it's that, the number of zeros moves 1, 2, 3. So I have 3 zeros. I move the decimal over 3 spaces. And there's the answer. And that's how we'd write it. Okay, an easy way of looking at this. If we had 58 over 100, the number of zeros tells us how many spaces to move the decimal left. Right now, 58 is actually 58.0. Since there's nothing behind it, it's all zeros. What this one says, I move it 2 spaces to the left. And there's your conversion. How about if it's over 10,000? So we have, okay, this is 497, 497 decimal. I move it to the left. 1, 2, 3, 4. 1, 2, 3, 4. So it's decimal 0, 497. It's typically acceptable to put a 0 in front of decimal numbers. So this would be 0.58, 0.04. So notice we are a base 10 number system. So when dealing with fractions, if you can make the denominator equal to a factor of 10, like 10, 100, 1,000, and so on and so forth. Then converting a number to a decimal only requires moving the decimal to the left, the number of zeros on the bottom. Remember we said if I had 72 over 10, so I have 1 0, the number on top is 72.0. Since only 1 0, I move it only one space to the left. All right, so what if we had 2 to the base 2 to the 6? Remember, we want the bottom to be a number of 10. So we have to figure out what do we have to multiply to the bottom to make it equal to 10? 2 times 5. How many 5s do we need? Well, we have 6 2s, so we need 6 5s. So on the bottom, since we have 6 2s and 6 5s, since they both have 6, they're multiplied together. And on the top we actually have 5 to the 7th. Because we have 1 here and 6, we add the powers on top. So 2 times 5 is 10 to the power 6. Okay, what's on top? We know 5 to the 6 is 15,625. So 5 to the 7th is we multiply by 5 again. 5, 10, 12, 31, 28. So it's 78,125 over 10 to the 6th. Remember, the exponent, if it's 10 to the 4th, that means there's 4 zeros. If it's 10 to the 6th, that means there's 6 zeros. So the number of zeros on a base 10 is determined by the exponent. But this one says, since it's on the bottom, move it 6 spaces to the left. So we have 1, 2, 3, 4, 5, 6. So they have to put another 0 in front of there. 0, 7, 8, 1, 2, 5. There's your decimal equivalent. Okay, what if we had a combination of 2s and 5s on the bottom already? Remember, we have to have this, the 2 times 5 is 10, but we have to have the same number of exponents. So since we're missing 1 more 2, we have to multiply 1 more 2 to top and bottom. We have 4 2s plus 1 more is 2 to the 5th times 5 to the 5th makes it 10 to the 5th. And 2 to the 1st is just 2, so 2 times 1 is 2. Move it to the left 5 spaces. So we have the 2 points. So it's 1, 2, 3, 4, 5. 3, 4. So the answer is 0.0002. Okay, what if I'm not giving to you as base 2 and base 5? For example, if we're just given a number, then the first thing you have to do is prime factorize it. What is 125 made up of? Since it ends in a 5, we know 5 goes in there. 5 goes into 12 twice. 5 times 2 is 10. That means you have 2 left over. And 5 goes into 25 5 times. 25 is made up of 5 times 5. So 125 is made up of 5 times 5 times 5. 5 to the third. So we're missing 2s. How many 2s do we need? Since there are 3 5s, we need 3 2s. 3 5s, 3 2s. So we have 5 times 2 to the third, which is 10 to the third. 2 to the third, 2 times 2 times 2. 4 times 2 is 8. So the number is 8.0 on top. But I move it to the left 3 spaces. 1, 2, 3. Means I need a 0 there and a 0 there. So my answer is 0.008. Okay, so 250. Remember, we want the bases to be 2s and 5s. Since it ends in a 0, we know it's divisible by 2. 2 goes into 2 once. 2 goes into 5 twice with 1 left over. 2 goes into 10 5 times. So it has 1, 2. 125 ends in a 5, so we know 5 goes in there. 5 goes into 12 2 times with 2 left over. 5 and 25, 5. So the bottom is made up of 2 times 5 times 5 times 5, which is 2 to the first, 5 to the third. We have 2 times 5, that's good. But we have different exponents. They have to have the same. So we're missing 2 more 2s. So we have to multiply top and bottom by 2 more 2s. So we have 1 2 here and 2. So we have 3 2s. And we have 3 5s. 2 times 5. They both have a 3 exponent. So it's 10 to the third. That's the bottom. 2 squared is 4. 3 times 4 is 12. Since it's on the bottom, move it left 3 spaces. There's a decimal. 1, 2, 3. So the answer is 0.012. All right, so that's if we have 2s and 5s on the bottom. What we're looking for here, remember, the first part we're looking is called terminating decimal. A rational number, any rational number, A over B, in its simplest form can be written as a terminating decimal if and only if, or I'll put IFF from now on, if and only if the prime factorization of the denominator only has 2s and 5s. Any other number on the bottom doesn't necessarily will, can make it non-terminating. For example, well, that's actually, it will make it because 1 over 4 is 0.25, but 4 is made up of 2 times 2. So yeah, any other number on the bottom will make it non-terminating. Okay, well, remember we did 250 earlier. It's made up of 2 to the first, 5 to the third. Since it only has 2s and 5s on the bottom, 13 over 250 is terminating or has a terminating decimal. 1 over 28. Well, 28 breaks down in 2 and 14. 2 times 7. 2 squared times 7. Since that's not a 5 or 2, it's non-terminating. Five over 6. 6 is made up of 2 times 3. Since 3 is not a 2 or a 5, it's non-terminating. So what do we mean by non-terminating? Non-terminating does not end. That could be 1 over 3. Could be 0.3333 forever, which we'd write 0.3 bar. Or it could be some number that says 0.25, 25, 25, 25, and it's always repeating. So it's 0.25 infinitely. This means it goes on forever. All right, let's see, let's see some more examples here. Okay, so that does it for the terminating decimals.